My name is Jaime Garcia, and as you already know, we are coming a team from Berlin. We are all working within the same project that you see here, Global Freshwater Biodiversity, Biogeography, and Conservation. It's called Global Bio. And this project has three big components. So the first one is to come up with freshwater habitat delineation globally. So trying to do some cluster analysis to come up with freshwater habitats all around the world. But we are also collecting databases of freshwater biodiversity, and Aphrodite will talk more about it. And we want to apply state-of-the-art machine learning models to map the diversity of aquatic insects specifically. And once we have these two big milestones, then we want to integrate that into the last point, which is applying novel systematic conservation network analysis. So like priority area delimitation for freshwater. These are the big three objectives. And of course, the first step to start working on that is to get all the environmental information, the basis that we need for all modeling analysis that will be done later on. So because we are working as a team, concentrated on pre-processing, collecting, and getting the data ready. And Malene and Aphrodite, they are the ones doing the fun modeling stuff. So that's why I call this presentation setting the scene from geodata to text data. So what I'm doing basically is grabbing all this geoinformation and doing some manipulation, deriving some new data, but everything will be put into basically tables, so text data that could be then grabbed for the modeling part that you will see later on. So what environmental information we are using? The most important one is this new data set coming out, hydrography 90 meters. And if you want to know more details about it, you can contact the main author of the paper, which is under review at this moment. But basically, very shortly, the main characteristics of this data set is that we have a very detailed stream channel delineation all around the world. So we have compared and validated this stream channel network with very detailed local data, especially in the US, and our stream network looks really, really accurate and very detailed. Based on that and other derived data, we have created the drainage basins all around the world. So we have more than 1.6 million. And for each of the stream segments of the whole stream network, we have created the corresponding subcatchments. So we have more than 726 million subcatchments all around the world. This is the most important set of data, but based on the digital elevation model and all derived data, we have created a list of stream topographical variables, also a 90-meter resolution, of course, like slope, gradients, curvatures, many of them. And also really nice for modeling is the stream topological variables. So we have information about the connection, the connectivity, the networking in the whole stream channel. So the stream network, the stream order, but we know if you have a stream segment, we know which one is the next one and which one is the one before. So you can do a lot of routing and new type of analysis. So we have all these data set that we are going to manipulate, to derive new data and extract into the tables. But we also are using land cover information. So we are using the ESA the European Space Agency land cover data. We have this time series. The resolution is 250 meters, but it still is good. Also climate data. In this case, we are using the CHELSA database and all the bioclimate layers that are normally used for this type of biodiversity modeling. We are also working with soils, and we are generating some distant related measures between some observations because that is helpful, or also included when you use spatial models to correct for what they call autocorrelation, spatial autocorrelation, and so on. So apart from the project that we are doing, we get a lot of demand from projects and groups outside of our institutions to share this data because they also are doing some modeling. So this is just an illustration of how the data looks. So if you see here, this is the stream network channels, all the rivers, and we have here in black, these are the main basins. There's 1.6 million, I told you, globally. And then within each of these basins and for each of these stream segments, so we have the subcatchments. So it's a very detailed data. And yeah.
So what are the colors that clustered colors?
No, this is just for illustration purposes, or just a random selection of colors. That was just to point out the detail and how big the subcatchments.
Categories or classes or anything like that, right?
No.
They have an ID, but
yeah, that's important to know. Each of these subcatchments have a unique ID, and that was a big.
over there is where I discovered the error of flow to 32 and that they mentioned. So be careful about it.
Yeah. So when we started to write scripts to extract environmental information from these data sets, we were discussing if it is better to create a list of scripts that when you require data, you just use the scripts and let them run, and then you get your tables for specific collection points that researchers are doing. Is it this approach better? So every time we get new data or we want to produce data globally, we need to take these scripts and run them, and then we got the tables. Or we should write some scripts that will generate some fixed tables that then are somewhere stored, and every time somebody needs information, we just collect based on the IDs, whoop, the information, here it is. So that goes immediately, because this might take some time and we need to run them again. So what is more effective, this or this? And I think we still don't know. So we have written a series of scripts to do this for people who are delivering some data sets, but we also are running this to create these massive tables that then can be easily used to extract the information. And this is being generated for each of these subcatchments. So for example, if we want to do this clustering globally, so we have this data already in place, so we can use the information to run that. And if we want to use those subcatchments as units of analysis, so we have the tables already there. So now we are transforming that with Postgres into a database, and Peter told me that then generating these tables is, we should go directly from the scripts to the Postgres, so we save a lot of space, and because the tables are then ASCII files in the Postgres binary, so something we need to think about. So I'm going to show you just chunks of some of the scripting procedures with illustration of some examples. Tell me if I'm running out of time. So this is one case where we get from other groups some data files, and they need to use the coordinates of those data to extract the information. So this is a typical example where you get some IDs for these collection points and some metadata information. But of course, the important things are the coordinates, which is what we use together with the IDs to start extracting information. Oh, that should have been before, but this is just for you to have an idea, and Giuseppe can explain better that for all computational analysis of the hydrography 90 meter data set that I told you at the beginning, Giuseppe created this irregular tiling system. So each of these tiles encompasses some basins, and for computational efficiency, I guess, it was necessary to do this kind of irregular splitting. We cannot do a regular splitting because then we cut the basins and then we cannot calculate all this hydrological continuity. So in each tile, we needed to be sure that the basins are contained so that we can run these things. And all the tables and the scripting I mentioned before, we are running for each of these tiles. We have 160, I think, or yeah, 166 or something. Yes.
I think I'm a little confused. Why do we have a tile over the ocean?
Like here, there are islands
Small.
and
Okay.
Yeah.
so one of the products of the hydrography 90 meters, this is another type of data sets where we don't get this table with the coordinates, but we have all the stream network, which is given as a vector file, a JPEG file. And for each of these segments, you have 1 point. So you can use these points as a reference as well to extract information. And this vector file, it comes together with lines and points. So just to extract the points, these are some of the scripting we are using in this case.
I think that's a graph that's shown on the top. We have information about the directionality of the water flow, right?
Yes.
And the volume of water.
Volume not yet. Next step.
That's the next
Speed
step.
of the river.
Next step.
Yeah. So to split this data into the lines and the points, which is the ones we need for reference, we use this OGR to OGR. So you have seen all the GDAL utilities, but OGR has very few. But actually, you can, within the OGR, you can use the SQL syntax. And this is really, really powerful to manipulate the attribute table that comes with vector data. So this is something we didn't learn during the course, but it's just very, very powerful how you can extract information. So this is something is really worth also taking a look and learning a little bit of the syntax. So it was just an example. So one issue we get when we get these points from other data sets is that if we want to do some analysis, we get this situation, yeah, where you have the stream network and these are the points you get. So you see that this point is not overlapping with the stream network. So this is a problem if we want to calculate things of this point related to the network. So we need to do the snapping, and that is not, there are functions that easily snap with the distance or other indicators. But when we have discussions with the experts who collected the data, they said, okay, if these points, if you make it with distance, this point will go here because this is a shorter distance. But talking to the people who did the collections, they said, okay, this point belongs to this subcatchment, the yellow one. So it should be snapped to the closest stream network location. So you need to take all this into account. And of course, for us also grass is the tool to use. Yes.
So you have information about elevation as well, right? So like, shouldn't that be determining which direction you should be going instead of just making the presentation accurate? You see what I mean?
Yeah.
Yeah, but quite often you don't have elevation. No, you have elevation. Okay, so but this point, you know, can be here, but we need to bring to the stream. Okay, so there are different ways to bring it to the stream considering the elevation and the flow accumulation, but there are always cases that you can have mismapping situation, but you don't know.
Maybe I don't understand what the snap stands for, but like we know that the water is not going to flow up, right?
No, the snapping is this, because here you collect the species, let's suppose, and the species water present, okay? But due to the mismatching in geolocation, blah, blah, the water is here, the river is here. So, but due to this alignment and so on, you need to bring this point and bring it to here to get all the water predictors information, okay? And this situation is not snapping to here or snapping to here is not always so straight. If the point is here, okay, fine. But if there are this kind of, it's quite hard to try to predict which one is correct, because you still also don't know. So, and this is, of course, if you snapping, for example, if you you consider the upper stream contribution, this river is very big, rather this one is just started. So this one can later on influence the model negatively, okay? So this is something that we are talking inside to the group, which is the best procedure, and we still don't know.
Yeah, so
it's quite complex to.
But still, we need to do that if we want to model water discharge, and this point is about how much water, of course, it needs to be in the river. Also, for some analysis, we need to measure the distance as the fish swims. So it needs to be snapped to the network to be able to measure these distances. Or if we want to create, I have an example of upstream basins, we need to do the snapping, and there are different ways, and we have a lot of discussions and different strategies to do that. But this is one example of a function in Bash that I wrote. You set some variables and the folders where you want to do things, and then here some variables. Again, you extract the point and the stream line. And then the nice thing is here, with this set of functions that Grass had, the vector network. So you put your stream, you put your point there, and then you connect based on distance. And the distance you specify here in this threshold. And the chunk here is just to calculate within this subcatchment what is the maximum distance. So you can specify here. And then you have this unique output where you have like different layers in the output. One is the stream network and the other ones are the points. And this is really nice because you can do a lot of topological networking analysis when you have this kind of data. So this is in Grass, also mixing things with Bash. And then you just get your output, it's just tables. And here is where the function finished. And because we have many points, so I get the IDs of those points, and then I can run the function in parallel using this parallel function in Bash, which is really nice. So you specify here 40 cores you want to use, you specify all the IDs and the parameters, and then you just let it run. This is really nice and very clean. You get a lot of tables that you then concatenate here, and then you got your new database with the new coordinates of the snapping points. It's really nice. So once we have done that snapping into the rivers, one of the other working groups, they require the upstream basin. So this is the point, this is the river here, and they needed to calculate this upstream basin because they think that everything that is happening here in the upper part has an influence of the habitat of the species here. So that's why it's important, for example, to do the snapping. So to calculate this upstream network, upstream basin also in grass, you read grass, and then the nice thing is here, they are water outlet. So you specify your direction that we take from the geography, the coordinates of where the point is located, and that's it. And then you get your upstream network. And with that, yes.
Yeah, just for clarification, because I understand that you guys still don't have information about the direction of the flow. So you do.
Yes,
Direction, yes. We have all parameter that physical parameter. So slope, aspect, direction of the water. What we don't have is the amount of water. Okay, because the water quantity we still don't, and water quantity and quality, but the physical are there. Okay. So we with computation that we do.
And this is something nice I wanted to show you. When you apply this function, of course, you are doing the calculations for the whole area because you need the direction of the whole area to calculate this upstream network. So the output is a raster file here with ones, and all the rest is no data, but you still have all the extension. And the next step was to make a crop. So remove all the no data and just leave this raster file. This is what I'm interested in. So in order to do that, this cropping, I was exporting the data, and then I was using, I was polygonizing the raster file so that I just get the polygon, and then I was getting the coordinates of the extreme, and then I was cropping. And even though in PC crop you specify the no data, the output loses the no data. So you need to run a GDAL edit. So I talked to him about it, and he's fixing the code. But now during these days, we just find out that you can here in grass make a zoom based on the output, and then you already do the whole thing.
Why you didn't ask before?
Because that was looking nice. That was looking professional, and so that's why it's commented out now. So it's just doing this, and you get the.
What's the difference between this zoom and using the mask in grass?
That as I told you, the output is just the raster and no data. And the zoom, if I specify this raster, it removes all the no data.
Okay, it's changing the extent.
And change the extent.
And I would do it with a mask.
Mask, you take it out, but the extent doesn't change. Okay.
So really nice. And then you make your output, and it's only for that extension. Okay, let's move quickly. Yeah, this is very easy. Sometimes we have this case. This is the subcatchment. This is the point, but this is our environmental data. We have a big pixel. So we just need to calculate the value at this point. And for that, so as we learned, we use the GDAL location info. You can use millions of points. It's really, really fast. I think internally it does it also in parallel. So it's really nice.
Maybe not.
Yeah, so this is an example of how the tables are. So you have for each subcatchment the ID, and then you have all the information of the environmental variables when you do this type of things. There is another table coming from the stream network vector file. I told you about it. And the same, you just use OGR to OGR to convert it to CSV file. So from vector to CSV, and then you do some cleaning, makeup, and with set, and then you see the table. So it's a really nice table because you see the topological connection here between each subcatchment, each stream network, and then you have different stream order measures and many more variables, flow accumulation and distances. So this is a really powerful table. And then to calculate, I told you we have the subcatchments and we need to calculate the environmental variables within each subcatchment. So we calculate some statistics, the minimum, the maximum, the range, the mean, and the standard deviation. And we do that also in grass using the univar. So also a really powerful function. Yeah, so you put your variables, your environmental parameter, let's say land cover, and then you use your subcatchments as the zones. So it's like a zonal statistics. And then you decide, he calculates more than this. But with OC, I'm just extracting these ones, which I'm interested in, and saving that in tables. And they look like this for one variable. So we also use land cover categories, it's the same. So we go to grass and we do we need to reclass the land cover because we have many categories. These are all the 22 categories we are using, but the original, we need to reclassify each of these based on these IDs. And then we run the univar again, here it is, and some cleaning, some makeup, and then you get a table like this. Anyway, these are the chunks. And this is the last one, which we are very proud of. So the output of this table, calculating the land cover proportion of each category within each subcatchment, is like this. So you have the subcatchment ID, you have the different categories for the different years from 1992 to 2018 for each category. And you have the proportion of that category in each of the subcatchments. So this is a huge table. It has, I think, 600 columns. And for each of the computational units, the tiling system, you may have millions and millions of rows. So Aphrodite wanted to do a subset of this table with only one category for all years. So category 130 for all years. Just a simple structure. And then calculate for each subcatchment the mean of all years. Very easy. So she tried to do that in R and it didn't work. Explodes.
How much it changed
No, we haven't done any exploratory analysis.
The land cover change, you know, when you go from urban to forest, forest to urban, agriculture to urban. So there are globally, there are few pixels that are in percentage. It's very small, the percentage of global land cover change. If you think about, you know, when
most often it's going to be constant.
most of the time it's constant. Yes.
In this case, it's still working. Keep track of that.
Yeah, because where you have the biggest phenomena is where you have big land cover change. Like for example, flooding. You take out a full forest and you have the flood. Okay, that's why. Good point.
So we came up with our knowledge and Google to this awk function to do this subsetting and calculating the mean. It's really nice. So with awk. So we get this, we wrote this function. So you at the beginning, you specify, this is a string with all the categories for all years, separated by comma, that's all, which you put it here into awk as a variable. And then at the beginning, so you run that just one time, you run this function, which is function in awk to split based on the comma, and then you save the categories with the years in this array. So in awk, awk has its own array. So this is an array. And awk has something which is called associative arrays that I didn't know, and it's really interesting because at least in R, when I think of arrays, you associate the array with an index. So in position 0, you have one value. But these associative arrays are like, it doesn't have the index, but for example, like you specify, this is my array colors. So one entrance of the array is red, which is equal to, I don't know, percent, the symbol, how is that? Yeah, hash, da, da, da. So, you know, it's a new concept, which is interesting. So I take just the header of the big table, and I'm storing in this array all the names of the columns of the big table. So this is in this array, IX. For the header, and then I left the header out, and I take the information and I run just through the number of categories I want in this array, and then I just extract from here the categories I'm interested in. So it's but it's really nice. And then after this is doing the subset, and then with the subset, you run you calculate the average. So you go through each row and you do the sum, and then you divide by the number of observations. And you calculate the mean, and this is what comes out. And this takes no more than 2 minutes for one category. So it's really amazing, this awk thing. Yeah, and this is how the output looks. So we have been running this stuff for months now, and you get, for one of the tiling systems, these are all the list of tables you get for all the different variables, and you see how big they are. And this tile is not that big, but you still have 185 gigas. So if you sum up the 200 tilings and the big ones, it's a lot of data.
The 100 is for the whole world.
No. This is for just one of the tiles. Just for one of the tiles. Yeah, we have terabytes of data. The good thing is that now when other groups are coming and saying, do you have information? Yeah, give us the database. We just grab from these tables, and we have in less than half an hour, and all the other people are, wow, you are fast. But this took, a lot of years of, Giuseppe knows.
Okay, very good. Next question. Joe.
How long it took the computational process?
Computational time.
Yeah. So
Years.
I mean, for the hydrography data sets.
That's curious.
Okay, for the hydrography, so for this paper that we just resubmit before to come, so will be out. You can already check the preprint. So during the review process, this is the beauty of be able to coding in a perfect way. I submit a paper, and we found an error. And Sami was already saying, "Oh my God!" I said, "Don't worry. One week I can repeat everything." Okay, but this one was a coding for 3 years. I was coding. Okay, so the scripting procedure need to be, when we talk with someone of you, reproducibility is not only when you publish it from yourself, because you need to rerun the scripting procedure several times, and from the beginning up to the end. And of course, all the scripting procedure need to be concatenated, okay? And as you see, maybe in other field, it's not really like this. We have a lot of pre-processing and the pre-processing can, let's say before to enter, pre-processing before to enter in the modeling, you need to really be picky in the pre-processing, because if not, you will get an output, you will get numbers, but this number then will influence in a bad way the modeling, okay? That can be a missing of no data, so no data well declared, that you have an outlier and you don't see because there are just few pixels. That can be mismatching, misalignment in the pixel value, especially when you work with this huge matrix. So over here that we have, if you start to have a little error in the matrix, in the pixel size, when you arrive to Australia, that you come up, everything you come up over here at 1 pixel shift, because my dimension of the pixel was not 20-digit long. Okay, I was just keeping 7-digit pixel dimension, but then I need, in my case, it was 0.8333, and I stopped it. It was 3333, because if you work in a small study case, the following one will not follow up. So try to be as much as possible picky in the pixel dimension, extension, masking operation, because if not, this data will come out later on, it will be there, and the modeling will find something. It's going to be influenced. So we have a lot of this preparation that is scientifically is not difficult, but it's technically that you need to really be picky, like I mentioned, in order to avoid and not to carry on. And of course, quite often you work with this so huge matrix that you just see the end of the procedure. You cannot zoom in on each single area and try to understand, and it's impossible. But as soon, for example, in our case, the stream order, that is stream order is nothing else. Okay, this is the first stream 1 and 1, this become 2, and this one become 3, this is again 1. So that one, it was the most picky one. So if the stream order was failing, means that there is something back that was not correct. But this one was really the last step. So I need to rerun this procedure several times. Okay.
Just to show me. Yeah, the scripting for the tables, it's been for 6 months or something, but now when we let them run, it takes just few hours, 3 hours, 4 hours. But this is because we are using the Yale
HPC
cluster.
Yeah, I wrote in the article how many hours is the full computation. Now I don't remember.
And we use a lot of parallelization, and we are learning. I mean, we do things sometimes the wrong way. So
and I get the email from
so we get emails that they want to close our user account because we are Aphrodite, that happened to her, that happened to me, and he's always receiving.
Why you didn't ask? Why you didn't ask? Just ask. You save time.
How do you guys validate that? Like the process of building all of these streaming networks is actually correct.
Okay, so for example, we have in the paper, now I can't pull it out, but we have another, yes. So this is the one that I built. Then there is another data set that is made by photo interpretation, only for US. So, and then, there will be another river here, another here, and then we calculate the distance between and the overlapping zone. I can show you the picture. So this one can be validated. Okay, not everywhere in the globe, but in the United States. Then you suppose that if in one area is working fine, because this is based only on the valley, the valley presence. We are mapping the channel of the river. We are not mapping water presence. Now, next step, where the modeling procedure is going to come, we are going to have volume, because here we have station, one here, one here, one here. So we are going to have volume, meter cubic per second, versus, sorry? Here we have gauging station. Okay, we're recording volume at monthly level volume, meter cubic per second, okay? And meter cubic per second water with whatever is influencing the water quantity. So raining, precipitation is going to be the important one, but then so retention, evapotranspiration, snow melting, you know, large rivers, small rivers. So that's why the physical properties are important for us.
That sounds like a pretty good application for graph neural networks. Have you guys considered that?
Sorry?
To use graph neural networks?
Yeah, actually, we talked once with you, and Sami is also reading about this graph neural network and so on.
It sounds like a really good application for itself.
Yeah, we need to arrive to the point, and we are close now that we have the data, you know, because it took 3-4 years to just prepare the data. Yeah.
Because right now you have these points of measurement kind of work as independent from solution, right? Like,
Bravo. Up to now, they are independent. We don't know where they are. Perfect.
so if you build a graph, you know, even if you have one point of measurement that's, you know, like noise and measurements, you can use the other one.
Yeah.
Connected to try to correct it, you know, like, so the whole system becomes way more robust.
Yeah, we have been reading a bit about it. And but now is, yeah, we will have the time to, we are in the second phase of the project, the modeling part. Yeah. Okay, very good. Any other question? Okay, cool.